Okay, good morning, everybody. It is time to start the last day of the 2026 Rubin Community Workshop. Wrap up those conversations. Yeah. Okay, thank you. That got people quieted down. We'll start with our everyday reminder that we do have a code of conduct. If you experience or witness any violations of it, please reach out to our code of conduct contacts. Also, for those of you on Zoom, you've been doing a great job staying muted. Thank you so much. Please continue to do so unless you're called on. And as a reminder, every single session has its own Slack channel where you can write down questions for the speakers. You guys look great. What a lovely group picture. Yes. Yeah. So thank you very much to actually, I don't know the name of the person who took the picture this year. Jacqueline. Thank you very much to Jacqueline and her drone for this wonderful picture. So if you want a copy, the slides are posted on the session webpage and you can go and grab a copy of this if you want. Lunch is happening again today. For the complimentary sandwich delivery, make sure between 10 and 11 you put your order in. Make sure you use the first name of Slack RCW delivery. And if you order and then you don't want your sandwich anymore, just let the front desk staff know that they can hand it out to someone else or get rid of it or anything like that. As a reminder, this is the first year that we're using the Friday afternoon of the RCW. So we've got special sessions on a research software engineering mini course, and then a session on Rubin 2036 is happening here in Kavli in the afternoon. And then over in Trinity, there's going to be a mentor training workshop happening. So please, if you're here in the afternoon, check them out. We're going to see how they go and if we maybe want to continue doing Friday afternoon hack sessions or something like that in the future. Reminder that there is a call out for new users committee members. Thank you very much to all of our current members. For new users committee members, it's by nomination, so either self-nomination, so volunteering, or you can nominate others that you think would be great members of this committee. They are due Friday, August 7th, and you can find the information about how to apply and how to nominate at that community post. And a big thank you to all of our chairs and all of the presenters. We had many contributed talks. The poster sessions are pretty much full every day. Amazing. Thank you so much for contributing. Chairing, especially at the RCW, is a lot of work because you're really in charge of your session and putting it together. So chairing, all of our chairs, very much appreciated by the SOC and everyone who attended. For the rest of our thank yous, I'm going to hand it over to Phil.
Right. Thanks, Melissa. You probably mostly already know this, but meetings like this don't just happen. It takes a huge amount of work over a long period of time through the year to put it all together. And it starts with these good people here who put a lot of thought into the design of the meeting, how to make it work well, figuring out the right sessions, working with you all to get those sessions together. So just leave this up here for a few minutes so you can recognize these people, and then if you run into them, you can say your own thank you for a really nicely designed community workshop. Many of these people will continue into future years, putting together this series of community workshops. So we owe them a thank you. One of the things I noticed this week during the sessions was that the word thank you is special when you're giving a talk. If you say thank you at the end, it triggers applause in the audience. So a good to remember. Let's see. Okay, here's an especially big thank you. Okay, I think some of you saw this photo, but not everybody did. I thought it was worth giving an airing. The data services teams worked incredibly hard in the run-up to this meeting in order to get EDP2 out and delivered on time, and time to be the first day of the RCW. And I think we can all agree that it was well worth their effort to do that, because it changed the way we felt about the meeting, and it gave a real jolt of energy to the proceedings this week. So let's say a big thank you to data management and data services for getting that. Okay, last one. We always say thank you to the support staff at the end of the RCW. They put in a lot of work pulling it together and supporting us all during the meeting, having already done a lot of work beforehand to get it together. Some of them come to this session, thank you. Some of them don't. They're already over there taking care of problems and so on. So this year we thought we'd do something different. We bought them a vase of flowers. It's out there at the registration desk. And there are some thank you cards that you can go and add your own note of thanks to. So we'll give them a round of applause now, but I encourage you to go and say thank you in person throughout the rest of the day. Thank you very much, Rubin support staff.
Thank you, Phil. All right, now let's just end with like looking towards the future a little bit. So for upcoming LSST at global workshops, we've got LSST at Europe 8 coming up in September, LSST at LATAM 3 happening in November, and LSST at Asia 2027 is planned for April of next year. So if you're interested in any of those, you can find them at these URLs, and also in the rubinobservatory.org website, there's a listing of all upcoming meetings, including the upcoming Rubin community workshops. If you want to keep coming through the future, the dates have been set for the next 10 years. And so, yeah, this is also available on the website, so you can mark your calendars now. This is what we're doing for the duration of the LSST. As you leave today, if you want to co-travel to your respective airports or train stations, you can arrange for that in the RCW Carpool Slack channel. If you want to ride share, taxi, do a rental carpool, or just co-travel on public transportation, you can organize that together. And then final message, we do have an exit survey. It's at ls.st/RCW2026. We're going to advertise it broadly in all of the Slacks and by email, so you'll get it multiple times. Responses by Wednesday, August 12th are very much appreciated. We really use this every year to make changes for the next year. So thank you very much for filling out that exit survey. All right, now we're going to move on to the project plenary. Every year, we celebrate some aspect of the Rubin Observatory project that has had a particular milestone. So we've celebrated EPO, the camera, we've celebrated survey strategy, and we've celebrated commissioning. And this year, we're celebrating the scaling up of LSST CAM processing to produce alerts and the EDP2. So today we're going to hear first from Eric Bellum, representing the alert production team, and then we'll hear from Colin Slater, representing the data management team and data processing. So thank you, Eric. Oh, yeah.
Oh, you got it? Full screen? Can I? Yeah, go for it. Yeah. Use full screen? Yeah. I think we can make it work. No, it's not. There we go. I think it's just slow to load. Is there a video? No, it's fine. It'll load here in a second. It's fine. I can start from here. Yeah, it'll be good. There we go. All right, we're good. All right, sorry about that, folks. All right. My name's Eric Bellum. I am honored and privileged to be the alert production pipeline group lead for Rubin. And I was asked today to talk a little bit about how we got to first alerts. And so unfortunately, or fortunately, you already know how this story ends. In February of this year, we issued public alerts to brokers
culmination of several decades of effort from a wide variety of people. So in thinking about how to tell the story today, I decided to take kind of more of a personal tack and a little more historical, and also to try to recognize a few of the folks who've contributed along the way. So I actually want to start a long time ago, back in the 1990s, which I thought was a kind of a good way to get into this question. So in the 1990s, one of the major questions in astrophysics was what was the origin of gamma ray bursts? The BATSI instrument on the Compton Gamma Ray Observatory was surveying the sky and detecting these high energy flashes all across the sky. And it was known that that high energy prompt emission came in two classes of short, of tenths to seconds, to long, tens to hundreds of seconds. But it wasn't yet known whether these were extragalactic or galactic, or what their nature was. And so there was a drive and motivation to try to localize these with longer wavelength counterparts, which required finer sort of arc-second level localization. And so ultimately that came in the late 90s with the detection of the first afterglows. This was driven by better localizations from a new generation of satellites, Babosaks and Hetty 2. But it also motivated the development of fully robotic observatories like ROTC that wanted to follow up where these localizations were happening and try to get contemporaneous long wavelength observations. And so to encourage that and to develop that, Scott Bartholomew at the Goddard Space Flight Center, who unfortunately passed away earlier this year, developed what was then called the Gamma Ray Burst Coordinate Network, or GCN. And this was one of the first sort of fully automated systems for exchanging astronomical information. You know, people know of the GCN today often for the sort of text circulars that people type up, but it's also a network that exchanges pointing information and triggers between satellites and ground-based observatories to enable rapid slewing and follow-up. And that, I think, inspired the community to go and think about how to generalize these ideas beyond gamma ray bursts. And so in the early 2000s, there was a movement to think about exchanging information from a wide variety of time domain events. And this led to the development of the VO event standard in 2005, lots of thinking about heterogeneous telescope arrays, and the start of the meeting series, Hotwiring the Transient Universe in 2007, which is still running today. There was a meeting just earlier this year that some of us were at. And that, of course, also influenced how Rubin developed. So Tony in 2002 is writing and talking about LSST data will be public, the transients and moving objects immediately. And in 2004, we have Michael leading the design reference mission development, talking about rapid analysis of the LSST image stream with prompt delivery of alerts. And then finally, in 2008, with the science book, we basically see fully formed the idea of alerts as we know them today. We're talking about release within 60 seconds of the shutter closing, sending postage stamps of the transients along with their past history, and an emphasis that the alerts are not going to be filtered. We're going to send everything that is 5 sigma in the difference image. And so this is the sort of conceptual idea of alerts as we know them today, but at this point it remained conceptual. I was not involved in any of this. I was in graduate school at the time. I was working on gamma ray bursts, but again, prompt emission. I was using a solar satellite called RESI to study prompt emission. And I was also flying balloons. This is an instrument called the Nuclear Compton Telescope, which is a predecessor of the NASA SMEX COSI, which will launch soon, I hope. And ballooning was one of the most formative experiences of my scientific career. Really an exciting and great experience for learning. I will say ballooning has its ups and downs. But nevertheless, I graduated in 2011 and was looking for a job and was kind of searching around, thinking about my options and thinking about going to work for Twitter or something like that. And then I was contacted by Sri Kulkarni at Caltech, who encouraged me to come there and start a postdoc working on a project that he was envisioning, where we take this very historic 48-inch Schmidt telescope that was used for photographic surveys back in the 1950s, and build a new camera for it that would fill the focal plane with CCDs and do time domain astronomy. So I did go there. I became the project scientist for what we now call ZTF, the Zwicky Transient Facility. And I spent a lot of time thinking about requirements and cost trades and how many CCDs can we afford. And you can see concepts of different focal planes from 9 to 16 CCDs. And we wrote proposals and we sought funding from funding and partners. And it was a little bit slow going, to be honest. We, of course, approached the NSF. They turned us down initially, but ultimately we were successful. And in the first Mid-Scale Innovations Program, or MSIP program, which sadly is no more, we were funded for a 5-year program. And this is text from that proposal, and we very explicitly pitched ourselves as a precursor to LSST, recognizing that ZTF would sort of be at the 1/10 of the alert rate of ZTF and be what Sri called training wheels for that jump and provide ground truth for classifiers. And we also emphasized sort of the community aspect. We hosted summer schools for graduate students and undergraduates, some of whom are still in the community now. We also said we would release LSST-style alerts. At this point, there are no real brokers in the sense we know them today, and no surveys are issuing, 5 sigma dia sources for every transient. I will say, I think I'm among friends here that when we put that proposal in, we didn't really know in a deep way what we were saying we were going to be doing. We just said, sounds good. So with that funding, the engineers at the Caltech Optical Observatories got to work. Particularly, I'll credit Rich Dekaney, the project manager, and Roger Smith, the lead camera engineer. Designed a really beautiful compact camera that fits inside the telescope tube and re-engineered this historic instrument to operate at a much higher rate than was ever contemplated in the photographic survey area. And so we built the camera. It's beautiful. Eventually, it was installed. Instrumentation projects take a long time, and so I was again on the job market, not finding many options. When I was contacted by Joko Ivizek, who encouraged me to apply for a research faculty position at the University of Washington to come and be the science lead for the alert production team that was being formed there. This was in 2017, so I accepted. When I got there was already a team that had been formed, and Simon Krukov, who passed away unfortunately several years ago, had hired a really wonderful collection of individuals. And it was really wonderful to be able to come and join such a talented and capable group that I feel like really bears the imprint of his personality. And I'm sad that he's not here to see this, but I hope that he's proud as he watches it. Among those folks was Maria Patterson. We had tasked Maria with working on alert distribution. And Maria encouraged us to look at a system called Kafka, which was coming out of the commercial internet at that time and is used for distributed event streaming. And she said we should look at this very seriously. And I would say that was not an obvious position in 2017. We've all heard of Kafka today, in part thanks to her efforts. But at the time, that was unusual. But she convinced us that this was worth a hard look, both for Rubin, and eventually we convinced ZTF as well. Maria was also influential because she encouraged me to think about a metaphor that we often use. So it was very common, and especially in those days, to talk about the LSST alert fire hose. She pointed out that this isn't a particularly welcoming vision of the alert stream. Suggests that you're overwhelmed, you can't handle it, you don't know what you're going to do. So she suggested we think about ourselves as building a fountain, a community fountain that everyone could come and share and play in. And that's something that I've kind of carried with me since that time as an idea of what we're trying to create. So we convinced the ZTF folks to try Kafka, and we needed to make a production system. And so in his usual way, Mario jumped into action and built us a production system in the cloud that we could use for distributing alerts to brokers should they appear. And so we put out kind of a call to the world to see who would take them. And thankfully, a number of groups did. I want to credit first the Las Cumbres Observatory, who built on the left the Mars system, making alerts really simple. Just a quick front end that allowed users to see the public ZTF data and play with alerts and start thinking about this. But later in 2018, we did start to get the brokers, as we know them today, joining. Lacer, Alerce, Antares, I think the first three, but then later hit Google, Fink, Ample, and others. So I think this really validated our intuition and certainly the NSF's hope that this would seed the broker ecosystem for Rubin. So we have brokers. Now we have to get Rubin ready. Oh, before that, I just wanted to highlight. So this is from ADS. It's an imperfect science, but I wanted to just pull out. These are the papers on the left and the citations on the right, just from users of the ZTF alert brokers. About 350 papers, about 3,000 refereed citations. And this is excluding the ZTF team entirely. So I think a very successful scientific enterprise through the years. All right, so the brokers are ready. Now we have to get Rubin ready. And so this, of course, relies on the whole project, but certainly Rubin data management. And again, too many individuals to credit one by one. We need middleware, we need computing, we need build systems, we need documentation, on and on and on. We rely on every piece of it. But I do want to highlight the specific members of the alert production team. So of course, alerts rely on difference imaging. Ian and Bruno have been our stalwarts in that area over the last years. We needed a high performance database that the pipelines could talk to and retrieve alert history within that sort of short timescale latency. And so Andy Salnikov provided a Cassandra system for us. We needed a real-time execution framework that would preload data and reliably execute the pipelines. And so KT gave us a concept, Christoph made it real, Shinfang and Dan have made it reliable, Aaron has kept it up to date, and Ian made sure everybody was staying on track. We needed real bogus, machine learning to tell artifacts from real astrophysical sources. Tatiana led that effort as a graduate student, supported by Fed, Masao, and Bruno. We have to get rid of satellites. Meredith told us where they are, and Bree got rid of them. Bree also helped maintain our alert system and our communication with the brokers. We need templates, as you've heard all week, and Aaron has done heroic work vetting tract by tract and patch by patch many coads so we could put them into production. And of course, we want to label and discover moving objects, and so Jake, Ari, and Mario have taken on that effort. And so none of this is any good if there's no data. And so of course, I can't credit everyone who built the observatory and commissioned it and operates it today. But certainly we watched with enthusiasm as we saw first light with LSST-CAM. And we waited impatiently last summer through August storms. But eventually by last fall, we had some templates in a few deep drilling fields. And we were ready to start sending some integration alerts to our partners, the brokers. And so you can see the Slack message here from early September of last year. And I was very gung-ho that we should go public as soon as we could. And the brokers encouraged us to take a little more measured approach, which was a good idea because they had a lot of feedback for us. They gave us excellent bug reports and identified many issues that we were able to deal with through last fall, some of which were pretty gnarly. So I'm glad they gave us that help. But by early this year, we were getting close to ready for public alerts. And so we went through a little dance trying to find the right date, and there were weather and other issues that delayed us. But eventually we had a date in late February. And I got this message from Phil encouraging us to set up a Zoom that would invite a large number of people to watch the first alerts come. And I try to avoid live demos in general in my career. They're pretty stressful. And doing one for a project we worked on for 10 years seemed especially challenging. But we did set it up. And we also, in our usual fashion, gave the brokers even less notice and invited them to come as well and share what they were finding. and it worked great. We set up the Zoom, we set up the dashboards, and we went on Sky, we focused, we took the first science image, we watched as prompt processing spooled up its workers, and then we waited impatiently for a couple minutes, and then we saw the uptick of the first alerts going out. And then we handed off to the brokers, who immediately started showing us interesting things they were finding in their interfaces. And it was really a hugely joyful celebratory moment. And for me, definitely a great source of pride. So you've seen already what's happened since then. We've been sending alerts as science images and templates allow since then, with a volume steadily ramping up with our template coverage. Xinfang also showed this plot of processing status, showing that especially the prompt processing frameworks and the pipelines are performing virtually flawlessly since we've started operations, which is a credit to the team that has built them. And science is happening. There's almost 1,500 transients that have been reported by science users of the brokers to the transient name server. And I think this really validates that whole end-to-end ecosystem. None of these are the Rubin team. This is all the science community. So I think, and I hope that I have sort of shown you that, alerts are the cherry sitting on top of a lot of effort from many people over several decades. And I hope that those folks feel equally well a sense of investment in this accomplishment. But I also want to say that, you are also a part of this. And, ultimately, Rubin's scientific legacy and the value of the alerts depends on the science users. And so I hope you'll take these data and go out and make discoveries. Thanks very much. At the end, so we'll hand off to Colin. It was supposed to be a picture of the group, but it didn't render.
We on now? Sounds a little bit better. So I was thinking like what it felt like through the past 6 months of processing the data release. And I realized that it really, like I have the same feelings about this as I did anytime that I've been observing or was lucky enough to be at the summit with Rubin, that you just get the sense that there's so many pieces of the puzzle that all need to be working like all the way through in order to make the whole system like deliver, like meet the goal that you have. Like to get on Sky, we need the telescope motors to be working. We need the cooling systems to be working. We need the computers to be working. We need the camera to be working. And we spend like so much time fighting all of these in order to get everything to line up to get on Sky. That all has to work together smoothly to get to the goal. And that's basically this. I have the same feeling about the data release processing. There's so many pieces that we have to keep working. So this talk is really, I think of this as kind of a follow-on to the science pipelines talk that was presented yesterday, where all of the developers from the pipelines told you about all of the algorithmic improvements, everything that they did to get the pipelines ready to process all of the data preview 2 data. And there's no way I can do justice to summarizing all the work that they've done. So I will just say, like, if you missed that session yesterday, you should really watch it, because that, like, the best way to celebrate their efforts is to hear from the pipelines developers themselves, tells the algorithms that they are all so excited about. So I'm going to pick up and talk about the production process, starting from when we had sort of the release of the pipelines we were ready to start production on, and getting that running. So one slide of background, just to make sure we're on the same page about how the data release proceeds. We go through basically 4 stages. We start by processing individual visits, to sort of a preliminary set of calibrations. We take those preliminary measurements from stage 1, we combine them in global calibration to get the best astrometric solutions, the best photometric solutions, PSF models. We co-add all that data in stage 3, we run detection on those coads, measurement on the coads, and then go back to the visits in stage 4 to do image differencing in light curves. And so when you think about doing a data release, you're probably thinking, oh, that's going to require like lots of CPUs, right? And that's definitely true. Like the amount of CPU hours that went into the data release, I can add it up, and it's 3 million CPU hours. That's like a big number. I can't do that on my laptop. I don't have a computer big enough. But I think it's important to kind of understand the context of that number. One way to understand that context is that with the size of the cluster that we have at Slack, 1 million CPU hours is something like a week calendar time, depending on efficiency. But that's still missing like a big component of the effort that goes into the data release. And that's the humans thinking about the data, understanding like, what am I seeing coming out of the pipelines? What am I learning from this? What is that weird thing that I just noticed? Like, is that a problem? Is that expected? Is that real? And that's really like where all of the time and effort goes, isn't into CPUs, but it's really into humans thinking about the data. And it's hard to like capture that. I can't, like, it's hard to like give you a statistic that shows you exactly how that works. I was trying to dig up some way to characterize that. I will just show that the pipelines team keeps like a running slide deck of everything they're investigating week to week, just to like share amongst themselves what they were investigating. There's over 270 slides in that slide deck, just from the start of production to the end. Like, there's so much that's going on every single week of that process. And so the reason behind this is that the data are still new to us. And they were really new to us in December. Like, there was still like so much we had to learn. The data vary in so many ways, way above and beyond what we'd ever done in the sort of smaller precursor surveys. So the variety of coverage, the variety of uniformity, the variety of image quality. We don't just have like the one crowded field and the one deep field and the one high latitude field. We have hundreds and hundreds of square degrees of every single one of these environments. And so that just amplifies the problem of now we have to solve all of these crowded regions, and not just like the 1 or 2 that we could focus on. And then we're still learning like we're still learning what unexpected things we should expect. There's still new issue, like we're finding it's a new observatory, so we're finding new things that we didn't think could go wrong but actually could, and like that, adding that to our set of checks that we're doing, things that we're looking for, things that we're understanding in the data as we go. So there's one visualization I can show you that kind of maps the entire process of the data release from start to finish. And this just sort of counting up the average number of CPU cores in use per day over the several month process that we went through for data release production. I've highlighted the different stages of the processing that I was talking about earlier here. Stage 1, 2, 3, 4 in different colors. And I have a few things I want you to read from this graph that maybe aren't super obvious. Some aren't even on the graph at all. And one of those is that all of these jobs that are running, huge credit to Huan Lin at Fermilab, who on the campaign management team was responsible for like taking the versions of the pipelines we needed to run, figuring out what needed to be run, how it needed to be configured, what was the best way to get it optimized to run on the cluster, and really made this go and kept the train on track. So many thanks to Juan. The other thing I want you to see in this plot is not necessarily the CPU hours themselves, but sort of the negative space in between all the CPU hours. Because like I was saying before, this is really like a human-driven effort. All of those times where we're not necessarily like running a huge number of jobs, that's the time that we're spending thinking about the data that we're seeing. And I did some completely scientific measurements of the fraction of brain cycles that went into the pipelines team, the campaign management team, and the data validation team, thinking about DP2 while we were doing the production. And this is the absolute accurate data of what we were doing this entire time. Like, there's no point where we're just like sitting back and like watching the data churn away. Like, every time where we've just finished some sort of stage of the production, we are looking at those results, we are getting ready for the next stage, understanding what we're going to be doing next. And that's like fundamentally because every stage is giving us so much more information. Like, the first time you run the global calibration tasks on the entire data set, you're just bound to learn so much more than you couldn't just extract from like a small test region. You find all the things that are weird outliers, the one day that something went wrong, like you find all of those. Same with the co-additions in stage 3. Like, once we have a coad, like now there's so much more to look at, so much more to understand. And this is basically the same as like what all of the science users are doing when we release the data. Like, suddenly you have so much more that you want to go learn from the data. It's not like we do the data release and then you just like turn the science crank and out comes the papers. Like, your first step is to go learn and understand and really like dig into that data. And that's what we were doing all the way through this data release process. That's the same process. So right, like these gaps in between the production are really the peak times where we're getting ready for the next stages and understanding what happened in the previous stages. It's hard to kind of summarize like the details of what that's like, because a lot of those are sort of like 100 minor things rather than 2 big things. But I will give you like just 2 examples that happen to have pretty plots that go along with them. 2 examples of issues that we were working during this. Just to give you a flavor of it, on the left, there's this one tract we found where it had tons of wideband images taken, but for some reason there was just this blob that was empty and none of those images got into the coad. And we have all these quality cuts that would normally reject images that had bad image quality or weird PSFs or something, and it didn't meet any of those criteria. Something else was totally weird for causing this hole here. And like, it takes time to go think, okay, is this a problem? Should I expect this? If I don't expect this, like, how bad is it? Like, what's the consequences of this? Maybe this is pointing to like a deeper bug that's actually affecting data elsewhere, and that's actually going to crop up somewhere that I need to, that's really going to be more worrisome. So we tracked this down. This turned out to be a matching issue in the astrometric solver that we're able to pretty easily work around and fix that. On the right, if you make a map of the stellar density, so this is the way you find stars is dependent on the PSF magnitudes and the aperture magnitudes. So this is really testing those magnitudes are giving you the same answer. We found these focal plane sized rings in the density map, and you do not want to see focal plane sized anything in the data, that's not good. So every time something like this shows up, a lot of us have a minor heart attack, thinking like, oh no, how bad is it? And this, like, we tracked it down, we understood what was going on there, we figured out what data would need to be reprocessed in order to solve this, so you didn't have this in the data release, and we moved forward. But like, this is just the flavor of things that we're continuously chasing through the data release process. So I'm going to move on to one more component of the process, which is that it's not just CPU time, it's not just thinking time, but we also have to think really hard about storage, because the pipelines produce lots and lots of outputs, like generated over 7 petabytes of outputs, including intermediate files, in the course of the data release. Many thanks to Brian Yanni, also on the campaign management team, who sort of keeps on top of our storage needs and our storage usage, tells us when we need to clean things up, make sure that we have the space available to run the production for the next stage. But this is really like a challenge for us to manage. And so in the start of the data release, we had something like 29, 30 petabytes total disk available to Rubin, and we'd use 20 petabytes of it on other things. So, okay, we have a good headroom here. We thought at the beginning, okay, we got the space. Let's go forward. So we run stage 3, and that uses up a lot of the space. And that's to be expected. That's building the coads, it's building the warps. They use a lot of disk space. So we understood that. We ran the initial part of stage 4, and that got us like kind of close to the limit. We thought, that's looking a little scary. We're going to do a big cleanup. We're going to delete a petabyte of data. So it turns out that if you tell all the developers that we need to clear out a petabyte, they suddenly find like random multi-hundred terabyte data sets they had left laying around on their like personal space. It's actually easier than you would think to come up with a free petabyte of data. Okay, so everyone gets to work, cleans it up, because we know we have to get ready for the next. We need to do a little bit more of stage 4. We need to do a little bit more of stage 3. We're actually this is actually close to finishing production. It's just a little bit more that we need to do. So okay, we clear out a petabyte of data. We say, good, we're good to go with the next stage. We do the next stage, and it's not shooting up, but it's also like, where's that 1 petabyte? But okay, like we still got margin here. Let's keep going. Let the cores go until we get a message from the storage team saying the disks are full. You will have to stop. And we're like, we were so close. We're so close to being done. Okay, but what happened here? Fortunately, Don Dorner, the storage lead for the USDF, explained it to us in all the detail. And I won't go into all the gory details here, but suffice to say that when you RM the file, it goes away. The user doesn't see it anymore. But the storage system actually has a long process that it needs to go through in order to recover that space and make it available. And that just hadn't been proceeding at the way that we had expected. We thought, oh, the number went down, we're good to go. And no, it wasn't. So that process, I don't remember, this isn't totally accurate, but I don't remember how many people remember Windows 95. I think of this like defragging your hard drive. Again, it's not exactly this. It's not the same, but it has the same feeling. So the storage team did a lot of work to solve this. They like moved data around. They did a lot of investigations into why the data wasn't being deleted as fast as you expect. At some level, it kind of makes sense why this process was slower, because when you like go to a commercial vendor and you buy a storage system, like that vendor is going to sell you on the high performance reads, and they're going to tell you that we have the highest performance writes for this multi-petabyte system, but they're never going to sell you on the high performance deletes for your storage system. And we accidentally expected that. So, but yeah, so Don and his crew were excellent about being very open about the problems they were having. They told us everything they knew. They told us even the things they didn't know what was going on. And that helped us really understand what we needed to do better. So we did solve that. And we were back on track in sort of a week, which is okay. We learned, and I think that's fun. I think that's the fun part of the project, is that we have to really solve problems at all layers of the stack, from the science algorithms all the way down to the hardware, to make the data release happen. And so we're all sort of on this journey together. And it, like, once you start to think about it again, you realize, okay, this actually makes sense. Like, who could have predicted that Rubin would have challenges with the data volume? Except that this has always been the selling point of the observatory for the entire history, was that we were a big data project. And so I think the message I see here isn't about storage systems. It's that, like, the big data is now. We are right now at the phase where the volume is really challenging, and that's going to continue to be a challenge. The data volume keeps going up, which is good. Already, we've taken many times the number of images that went into DP2, and like, this is like, we're just going to be taking more and more data. This is all just going to be getting more and more challenging. So I will wrap up here, and just to say that I think we're getting better at the data production process while the problem is getting harder and our scientific standards are getting higher. What's with the and we're going to be on this learning curve for a long time, because this is not letting up. This is not going to get easier. For a while, it's going to get harder. And I think that's the fun part of this project, is that we still have challenges in front of us. And so lastly, I'll just wrap up and say that congratulations and thank you to everyone who made the data possible and made the data release possible. Thank you.
Okay, thank you very much for both of you. Don't go anywhere. We have time for questions. So Eric, if you want to come back up, maybe we'll do questions for both of you at the same time. I think we have, yep, one mic runner and another one over here. Perfect. Okay, questions. Please feel free. Jelko, do you need us to stand closer together? Are you taking the picture?
You're hidden behind the thing.
I got one. Thank you. Tremendous talks, tremendous. Thank you so much for all your work. Both of you had like dramatic, cool pictures at the ends of your talks, and they didn't show up. What were they?
I didn't have a picture.
Oh.
There was no slide there.
Oh, there was no slide there on your end. Okay, but Eric, you had something.
It was the conference picture.
Oh, okay.
Because I want you to go out and make discoveries with alerts and complete this relay race that we've been doing for 20 years.
Okay. Well, thanks, guys. Really, really awesome stuff.
Sorry to disappoint to not have a cool picture.
I'm curious about, well, the number of CPU hours is humongous. I'm actually surprised you can fit them all in a class or more. I wonder if, like, in the future of the survey, there is any plan to switch over to GPU, or not at all, or that just wouldn't work for the type of pipelines that you have produced?
Everyone's like constantly on the lookout for ways where GPUs could solve particular parts of the puzzle. It's like, our baseline assumption is that it would probably be some sort of like niche component that we would put on GPUs first. And like, there's been lots of efforts, some that have tried, and I think we're not at a point where we've seen the real benefit yet, but we're trying.
So for the AP case, it's tricky because, you know, right now the processing is parallelized by detector. So you have 189 processes. It's pretty pricey to get, and you need several chains to process in parallel as the images are taken. So you can't really get one GPU per detector. So then you're looking at some kind of central pool that you're exchanging data from. And so like, there may be speed gains there, but we're adding a lot of overhead and complexity. And at the moment, it's not obvious that those, you know, that is a trade we want to make, but that could change.
Hi, yeah, great talks. I'm just curious, how much of the alert processing happens at the summit versus at USDF?
It's entirely USDF. There's processing that helps the observers at the summit, but all of the alert processing happens right here on campus.
Michael.
And indeed, on that last question about the processing at USDF, has transfer from the mountain to the USDF been flawless? Has that been a source of concern? Is the latency what we've expected?
Latency is very good. We solved a lot of problems early in when the systems would sort of fall offline and would need some kicking to bring them back online. I think we're at the point now where the dominant reason why transfers wouldn't happen is because of the physical fiber itself falling offline, or one of the infrastructure provider for the place where we only have a single fiber route. Sometimes their systems, I think, have been problematic, but I don't want to say that it's minor, but it's the place where we only have like there's only a single fiber, and so there's not much we can do other than like maintain that fiber and keep it running.
Thank you, Colin and Eric, for this great talk and for also highlighting all the people who've been working on each step. This is something we never find out. And so thank you for telling us all about it. This peek behind the curtain was wonderful. I have a small question to Colin about the cellar density maps with the coffee cup shaped stains. Could you tell us a little bit more about what went in there and how you figured that out?
It's kind of a deep dive that's probably better offline. I think we saw hints of this in many different places. There's things that weren't quite right, but like when you see just like a little piece of it and a little piece here and a little piece there, like you kind of don't know if it adds up to a big problem or a little problem. And so I think it kind of gradually grew and grew that we were realizing like how much that actually was affecting things. I think the short answer of explaining what's going on here is that it was a mismatch between what images were used to build the PSF models and which images were used to build the COAD, like that COAD pixels in certain places based on the various masks that we had in building those COADs.
Thank you.
We do have more time for questions. I'd like to invite anyone on Zoom or in Slack. I have not seen any questions posted or hands raised, but now is your chance. And also, I'll take the opportunity to call for more questions from junior folks as well. If you're junior and you were thinking of asking a question, you're being invited to. Okay, let's thank our speakers again. Thanks, everybody.